Okay. Reaction rates. So for those of you taking calculus, you're gonna see a lot about rates. But what does rate mean? If I said the rate of something, how fast it's going. It's some sort of change over time. That's what a rate is. All right. We'll just say the speed which any quantity is changing. So if you wanted a mathematical formula, delta change in amount over change in time. Rate is always per unit of time. Now, what that unit of time is can be whatever you want it to be: seconds, minutes, hours, days, years. Doesn't matter. Okay. So there's lots of different ways. Or sorry, hang on. Let's look at some examples. No, let's go down. All right. How do you measure reaction rate? All right. So if we look at this little reaction right here. Zinc solid plus hydrochloric acid produces hydrogen gas and zinc chloride aqueous solution. What are some ways that you could think of to measure the rate of this reaction? Anything. I'm not asking you to tell me how to measure stuff, just what units could you use to measure something. Like, I'm not looking for you're going to use a eudometer to do whatever, but. Sorry? Changing in the energy. I'm looking for something like if we were doing this reaction in a lab, and I put it, okay, the units would be seconds, but what are we measuring? What would we measure? Look at this. This is a solid, right? So we could weigh it at the beginning, and then you can weigh it at the end, right? After measuring the time. And it could be grams per second, which you could convert to moles per second, right? If you have a solid, I'm going to write moles. You can weigh out how much the zinc you have, dump it in the reaction, let the reaction go for a certain amount of time, fish it out, reweigh it, and see what the difference is. Okay? And then you'd know the change for us, it would be the change in the grams per whatever unit of time you want. Okay? So if you have a solid, you can measure the grams per second or grams per minute or whatever. Okay? What else could you measure here? Let's look at this one. Gas is being produced. So you could measure how much gas is produced in liters. Okay? Liters per second or whatever. Liters per hour. I don't really care. So if you have a gas, you could measure it in liters per second. What about HCl? What is that? What is HCl? That's an acid. Now you don't really do a lot of it in chemistry 11, but acids have what? High or low pHs? Low pHs, right? So is the acid being produced or is it being used up? It's being used up. So what would happen to the pH if you were monitoring the pH? The pH would go up, right? Because the acid concentration is going down, so the pH is going to go up. Okay? So you could monitor the pH. Because the hydrogen gas is like going to bubble off, right? Well, that's a good question. If it's an open system, okay, what if it's open? Open system. What are we losing? We're losing the gas. So is the mass of the system going to remain constant? No. So what are we going to monitor? We can monitor the mass of the whole system, right? If it's an open system. Open system. mass will decrease because H2 gas is given off. So you can measure, you can put everything into it, weigh it all out at the beginning. You have a mass, let the reaction go. We're going to lose a bunch of hydrogen gas, weigh it at the end, and then you have the difference in how much hydrogen gas you lost, right? Or in the whole system. What about if we had something like this? What if it produced heat? What would happen in the beaker? It's going to increase the temperature, right? So that kind of goes to what you were saying. We can monitor the temperature change. Okay? So we could do, I don't know, I'll just write degrees Celsius. Degrees Celsius per whatever, minute. The point here is there are lots of ways to monitor a reaction. Okay? It's going to depend on what equipment you have, what is simple to do, and basically just what do you want to do? What are you looking for? Okay? You can measure color change as well. You need some special equipment to do that. Energy produced. If it's a closed, so in an open system, the mass is going to go down. If I close the system, you know what I mean by open and closed? Like open is just a beaker. Yeah, well, you can see the steam is coming up. That's an open system. If I close that, if I put a lid on here and heat up the water, what's going to happen? Why is it going to explode eventually? Pressure is going to increase. So if it's a closed system, you can monitor the pressure because we're producing a gas. Okay. All right. Now this system, the pressure would go up, right? Because we're producing a gas. But if you had gases over here producing liquids, the pressure would decrease as the reaction went. Okay. So it's not just that it's always going to go up. Okay. Okay, they've kind of did that. All right, we're going to do a lab later this week where you're going to measure the reaction rate, okay, by using some of these. Well, most likely to be a gas that you just measure the volume and a stopwatch. We just did that, so we don't need to do it again. Okay, and we will calculate reaction rates later on. But right now we're going to look at how to change the rate of a reaction. So, do we have this page? Yeah? We do? Next page, we have it? It's a different color. Oh, okay. As long as we have it, though, that's... Okay. So, we've looked at... Yesterday we looked at what we called spontaneous and non-spontaneous. Don't have to write this down. Assume these scales are the same. I know my drawing is awesome. Which one would be spontaneous and which one would not be spontaneous? Yeah. So this we would say is spontaneous because why? Has a lower activation energy, right? This one has a higher bump to get over. Okay. So some reactions go really slow, some reactions go really fast. We want to look at ways that we can increase the reaction rate or change the reaction rate. Okay. And there's a variety of things that we can do. All right. So the easiest, I don't want to say easiest one. The most basic one, I guess, would be to just increase the temperature. Okay. Why would increasing the temperature change the reaction rate? Sorry. There's more collisions, right? More collisions, and what else? You need two things for a reaction to happen. What two things you need? You need collisions and energy and correct geometry. So the more collisions you have by increasing the reaction rate means there's more of a higher probability you're going to have enough kinetic energy to break the bond, and say they hit, but it's not the right geometry, because the number of collisions is increased, you're going to have another collision where there is correct geometry. Okay, so you're just increasing the probability, essentially, is what's happening. So if we have kinetic energy, we get increased number of collisions. The frequency, I guess we could say. And we have more kinetic energy, which equals increase in chance of breaking bonds. And both of these lead to increased number of effective collisions. So increasing the temperature should increase the rate of the reaction. And in general, all right, every 10-degree increase, this is not a hard and fast rule, it's sort of a guideline. Every 10-degree increase will double the rate. Okay. Let's see if this is true. Before we get in kinetic energy distribution. Okay, here we go. Kinetic energy distribution curves. Okay, we're going to go into the weeds of theory here, people. Theory time. Yeah, but this is going to get a little theory-ish. Nah, I like theory-ish. I'm going to go with theory-ish. All right. So we know that every reaction has a minimum amount of energy I'll say kinetic energy required to break the bonds. This is called the threshold energy. Okay. So the threshold energy, as the name implies, is the threshold you got to get over to break all the bonds. Okay. If you draw out, don't use all the space. So you're going to leave yourself like, say, a third of it. I was going to do that. Okay, so leave yourself about a third to draw what I'm going to draw. Or at least a third. This is number of particles. This is kinetic energy increasing, going that way. And this is the threshold energy. Okay. At any temperature, okay, you will have a certain amount of molecules. They'll all have different amounts of kinetic energy. So there's this distribution like that. Okay. So this is a distribution graph of the number of molecules and their kinetic energy. All right. The most number of molecules sort of in the middle here. Where are the molecules that have enough kinetic energy to react? Yeah, they're on this side of the threshold energy. So the only ones that have enough energy to react are these here. So particles, I'll call them molecules. I'll just, whatever, particles with enough kinetic energy to react. They exceed the threshold energy, and if they collide with the right geometry, you will get a reaction. Most of the molecules are over here. Okay? Now, what if I increase the temperature like I did here? I put one of these on a hot plate, that one, the hot one, and I increased the kinetic energy of the molecules. So what happens to this graph if I heat up the molecules? How does it shift? It's going to shift this way, all right? We're not doing math, but yeah, essentially. So the distribution changes. It looks like this. Now, these are all just sort of rough estimates. Okay, so this is the higher temperature. This is the lower temp. Okay. I want to be clear though, the volume under this curve is equal to the volume under the pink curve. Okay, we haven't increased the number of molecules. We've just changed how the energy is distributed in the molecules. Does that make sense? Or we increase the amount of energy within the molecule. That's why more molecules are now over here. So now you can see there's more molecules, all the stuff in this area. So you have more molecules that are able to react, hence you get a faster reaction. Okay? So I can just write it right here. Higher temp equals increased percentage of particles with enough kinetic energy to react. Okay? Whereas the initial one, the pink one is the water I didn't heat up. You only have a small amount of molecules, so it takes its time. You heat it up, you have more molecules with a higher kinetic energy, which are past the threshold, therefore you get a faster reaction because more molecules are reacting. Okay? All right. Now this is sort of a side note because a lot of books and stuff kind of equate kinetic energy and equate threshold energy and activation energy. They're not technically the same thing. Okay? If you look at a potential energy diagram, doesn't matter if it's endo or exo. Where's the activation energy? It's from where to where? And the what, sorry? And the peak, the activated complex. So it's right here, right? This is the activated. That's the EA. That's the activation energy. Where's the threshold energy? What do I have to get over to break bonds? The top. That's threshold. energy. Why are activation energy and threshold energy not technically the same thing?
Because like activation energy is the only energy required to go from that threshold.
So activation energy is the amount of energy you have to add. Basically, like all the molecules here have an average kinetic energy if you averaged them out, right? Activation energy is how much energy you have to add to these molecules to push them past the threshold. Okay, the threshold is like set. The threshold is from here to here, all the way to the top. It's like it's that distance. So say it's like 100, just to be simple. That's 100 kilojoules. The threshold energy is 100 kilojoules. That's what you need to break the bonds. If you start at, no, I don't want to use 50. Whatever, 40 kilojoules. What's the activation energy? It's 60. So essentially, the 40 is like the average kinetic energy, if you want to think about it that way, of all the molecules. And then you add another 60 kilojoules to push them over the threshold. The threshold stays there. Okay? Now there's things we can do to alter that later on. But right now, the threshold and the activation energy aren't technically the same things. A lot of books just act like they are. And it for our course, it doesn't really matter that much. Okay? But just be aware that they're not technically the same thing. The threshold is the total distance. The activation energy is how much you're adding to bump over that hill. Okay? All right. So what determines threshold energy? What's going to determine that? That's what threshold energy is, but what's going to determine where it is? How strong the bonds are. So it's going to be different for all the molecules. Okay? So in chemistry, we would say is determined nature of the reactants. In other words, how strong are the bonds? Okay? So if we look at two reactions, we have nitrogen plus magnesium. I don't really care about the products. And we have iodine plus magnesium. Okay? I don't care about the products. All right. How many bonds does nitrogen form? I heard somebody say it. We need a periodic table at the front here. You can look right at.
What's the question?
How many bonds does nitrogen form? 3. It wants to form 3 bonds, right? If we look at data booklet. See? Well, nitrogen. It wants to form 3 bonds, right? Why does it want to form 3 bonds? 1, 2, 3. Because then it's got a full valence shell. So nitrogen wants to form 3 bonds. So if you look at the N2 molecule, this is a triple bond. And if you remember chemistry 11 when you did, what do you call the diagrams? No, what are the Lewis structures? That's nitrogen gas, right? That's a triple bond. Okay? How many bonds does iodine want to form? 1, right? If you look at, here's iodine. Where's iodine? There it is. There's iodine right there. Just picks up 1 electron and we're happy as xenon, right? So it only wants to form 1 bond. So I2 looks like that. What is going to be hard? I mean, okay, if you want to put all the electrons in there, then there you go. All right. We only have to break one bond. We got to break 3 bonds. Which is going to be harder? The 3, right? So if you're doing this energy diagram, with number of molecules, and this is kinetic energy, and they're at the same temperature. Which one of those lines is a threshold energy for iodine, and which one is a threshold energy for magnesium or nitrogen?
The green one is nitrogen. The green one is nitrogen. Yes.
Iodine is pink.
We said the same thing.
In reverse. All right. So the lower one, it's got a lower threshold iodine because you're only breaking one bond. So it's going to have a lower threshold energy, right? That's the I2 threshold energy. That's the N2 threshold energy. So how strong the bonds are determines the threshold energy. If you have a triple bond, that's going to be harder to break than a
Single.
Thank you very much. And then double bonds, etc. Okay. Is that okay? That makes sense? All right. Flip the page, please. I don't know. Do you? Every time now, I'm going to be like, do we have the page? Do we have this?
No.
Don't be mean. Okay. Concentration of reactants. When I say the word concentration, what am I talking about in chemistry? Moles per liter. How much of the stuff is there, right? So if you have a higher concentration, why are you having more collisions? There's just more stuff to bump into, basically. That's all it is, right? This is like, I know we talk about chemistry, might be complex and stuff, but really it's just like things smacking into each other. That's really all it is, all right? So if you have more things in a smaller space, they just hit more often. And if you heat it up, they have more energy and they smack into each other more often. That's it, okay? So if you increase the concentration, we're going to increase the rate. If we're talking about solutions, most likely it's going to be aqueous in water. Concentration refers to, what are the units? Moles per liter. Molarity, which is moles per liter. If you talk about gases, usually, if you're going to increase the amount of gas in something, you're talking about increasing the pressure. Okay? And you'll see in the second unit, we talk a lot about this when we do equilibrium. So, okay. So you can change the concentrations of gases in aqueous solutions. If I want more Alka-Seltzer in my water, I just dump more Alka-Seltzer in the water. If I want more gas in the room, if I could seal the room, I could just pump more gas into the room. Okay? All right? Oxygen gas, it would be nice. Okay? All right? You cannot change the concentration for solids. Because what is the formula for concentration? Moles per liter. It's dissolved. All right? So if I dump more rocks in there, I don't increase the concentration of rocks because the rocks aren't, I guess you could argue they do over time. But anyway, they're not really dissolving. All right? So you can't change the concentrations of solids and pure liquids. Only change the concentrations for aqueous solutions and gases. All right? So if I was you, sorry? No, density is the mass per volume.
But isn't like density like a type of concentration? Like how much mass is concentrated in a volume?
Like, I'd increase the concentration of rocks by really smushing the rocks together.
So what's a pure?
That's like a metamorphosis.
So you're like Earth. You're the internal.
What's so? Well,
You melt rocks together. Okay. For our purposes, highlight that.
what's called? What's a pure liquid?
What do you mean? What's a pure? It's a
What is a
pure,
pure liquid?
like water with nothing else in it is pure.
What's another example?
Pure. You could melt gold, liquid gold, right? Just pure. It has nothing else in it. Okay. All right. What are we at? We go to. Let's just burn through these, and I'll do the demos tomorrow. Okay. Pressure. All right. Shh. So we could change the pressure. Okay. But this is only going to work for reactions that have. No, you can't write in highlighter. Gases as reaction or as reactants.
You missed an S in the gases.
You can spell it both ways. Just like you can spell sulfur like this or like this.
Okay, but the pH looks better. Imagine.
What, the pH and the F? Yeah, you can spell it both ways. You can spell it both ways, people. You can have a preferred way, but you can spell it both ways. All right. Do you want the two S's?
Yes.
There you
Please.
go. All right. You got the two S's. All right. So you can.
I also thought that.
What?
Nothing.
So if we change the pressure and the volume, these are essentially the same thing. So if I have a gas here that's floating around, and I don't add any more gas, but I change the volume. So I squeeze them down, right? That is jacking up the pressure, okay? Because it's per unit volume. So if you shrink the volume, you're increasing the pressure, which is increasing the concentration, okay? Which means these are all closer together. They can smack into each other, and you get more reactions happening, okay? So increasing the pressure, which is decreasing the volume. So this is a good test question because I can say, what happens to this reaction if you decrease the volume? And then you got to think, well, decreasing the volume is going to increase the pressure, which is going to make the reaction go
Slower.
faster.
Yes.
Increases the rate. All right. Decreasing the pressure, which means I'm increasing the volume. So we're going from this, where they're really close together, and then we open it up, and the molecules go really far apart. They don't smash into each other as often. You get a slower rate, a decreased rate. I've been talking for a long time.
Don't worry, we love them.
I'm going to stop there, and I'm